Section 9.8, Power Series. In the previous section, we learned that certain types of functions could be approximated by higher degree polynomials, and the higher degree of the approximating polynomial, the more accurate the approximation. Now we will see that several types of important functions can be represented exactly by an infinite series called a power series. The definition of a power series says, if x is a variable, then an infinite series of the form, series that goes as n goes from 0 to infinity of a sub n x to the n, is a sub 0 plus a1x plus a2x squared plus dot 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 plus a n x to the n plus. This is called a power series. Generally, a series of the form n goes from 0 to infinity of an times x minus c to the n is a0 plus a1 times x minus c plus a2 times x minus c squared plus dot 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 plus a sub n is x minus c to the n plus dot dot dot. It is a power series centered at c, where c is a constant. So when you see it in this form up here, we know that we are centered at 0. All right, so when do power series converge? For a power series centered at C, precisely one of the following is true. It converges only at C, the series converges for all x, or there exists some r that's positive, that is a radius of convergence, such that the series for x minus c absolute value is less than r, and we know that that means that x minus c is less than r and greater than negative r, converges, so an r that's positive such that the series converges for this condition and diverges for this condition. So if we are a certain distance away from where our series is centered, and that is less than the radius of convergence, then our series converges. If that is greater than our radius of convergence, then the series diverges. Now, in part 1, right here, the radius is 0. In part 2, our radius is infinity. That makes sense. Why would it converge for all x? It doesn't matter how far away I go from the place that the power series is centered. It converges for everything. The corresponding domain is called the interval of convergence. In other words, the values you can choose for x so that the series will have a sum, a finite limit. For the examples in this section, please listen all the way through, and I will let you pause to write down the work. Find the radius of convergence and the interval of convergence. Be sure to check the endpoints. So here's our series. N is 1 to infinity, negative 1 to the n plus 1, x minus 2 to the n over n times 2 to the n. So to test convergence, we're going to look at what is the easiest test we know. It's going to be the ratio test. We don't need our negative 1 because we have absolute value bars. So the limit is n goes to infinity of the n plus 1th term over the nth term. At least write this as the limit is n goes to infinity of x minus 2 to the n plus 1 over n plus 1 times 2 to the n plus 1. So everywhere we had an n, we're going to write n plus 1 times, divided by this means times the reciprocal. Now this is important. Since it is n that is going to infinity, it does not affect the x terms. So we can pull out the factors involving x, but we need to keep the absolute value bar because we don't know what x is. Okay, and we're going to be looking at this interval of convergence and radius of convergence, so we need to maintain the absolute value bars. So what we can see is x minus 2 to the n plus 1, x minus 2 to the n. It's going to leave me with one factor of x minus 2. 2 to the n plus 1 is going to cancel with 2 to the n, leaving a factor of 2. Okay, so I have x minus 2 on top. N can't cancel with anything. I have n plus 1. And since I don't need to keep the x minus 2 inside, let's bring it outside. Also, I can bring that factor of 2. So now we're looking at this. Now, we've had plenty of experience with this before. We know that the limit as n goes to infinity of this is 1. Well, isn't that beautiful? Now, what is it that we want? So we want to know what values of x causes x minus 2 absolute value divided by 2 to be less than 1. So I want to solve that inequality. Now, what values of x causes the absolute value of x minus 2 over 2 to be less than 1? Which also means multiplying by 2, the absolute value of x minus 2 to be less than 2. What I can tell here is that we are centered at 2. So that makes my radius to be 2. So we are wanting to converge by the ratio test, which means we need this to be less than 1. If we recall, all of this needs to be less than 1 for convergence to occur. So now I'm at that place. Now this is what is left, and I need this quantity to be less than 1 for convergence to occur by the ratio test. Take a moment and write all of this work down before we continue this problem on the next page. Okay, this example continued from the previous page. Here was our series. We got down to this part, satisfying the ratio test for convergence to occur. This would not need to be less than 1. And we know that we can write this inequality like this. Well, we know that this means x minus 2 is less than 2 but greater than negative 2. And if I solve this, I get x to be greater than 0 and less than 4. Now, just as an aside here, let's look at the mathematics involved in this. If you recall, earlier in the year, I told you it was very important to understand how to write absolute value functions in a piecewise manner. Remember that absolute value when something is not negative is itself. When the x is less than 2, the quantity inside is negative, so the absolute value of a quantity that is negative is the opposite of that negative quantity, the opposite of itself. That is why we have all of this. Remember this? Now, a very important thing here is this is possibly the interval of convergence, but we have to check endpoints. Okay? And so checking endpoints means I need to know what is happening in my series way up here when x is 0 and when x is 4. So to check convergence at the endpoint, we're going to let x equal 4, and we are going to substitute 4 into our series. Now, our series was the series as n goes from 1 to infinity of negative 1 to the n plus 1 times x minus 2 to the n over n times 2 to the n. And everywhere we have an x, we're going to substitute 4. And then we're going to simplify this expression and see what we get. So this is going to give us negative 1 to the n plus 1 times 2 to the n divided by n times 2 to the n. Okay, we can see the 2 to the n's cancel, and that leaves us the series as n goes from 1 to infinity of negative 1 to the n plus 1 over n. Now, what do we know about that? Guess what? That is an alternating series that we know converges by the alternating series test. We know that 1 over n, that a sub n, is positive. We know that the limit of a sub n is 0, and we know that the n plus 1th term, which is positive, is less than the nth term. So we know that this series converges. What does that mean? When x is 4, I have a converging series. So 4 is included in the radius of convergence. Note, on the AP test, show all properties of the alternating series test. Very important. Now let's check the other endpoint. That is going to be when x is 0. So everywhere we have an x, we're going to substitute 0, and we get this. Now let's look at negative 2 to the n. That can be written as negative 1 times 2, the quantity to the n. When we do that, we get this negative 1 to the n plus 1, this negative 1 to the n. Notice that is negative 1 to the n plus 1 plus n. Then I have my 2 to the n. The 2 to the n's cancel. -1 to the n plus 1 plus n gives me -1 to the 2n plus 1. These cancel over n. What we know about 2n plus 1 is it is always odd. So we do not have an alternating series. Very important to notice that. So now this is our series. That -1 can be brought out in front. What do we know about this? This is an harmonic series. We know it's a p series where p equals 1, so it diverges. So my interval of convergence for this series does not include 0. So the interval convergence for this series is x greater than 0, less than or equal to 4. Take a moment to write down the rest of this example. Here's the bottom of the page of the rest of example 1. The AP exam always has a question on intervals of convergence. Pay attention to whether you are asked for the radius or the interval of convergence. On some AP tests, most students did all of that work we just did, but could have stopped at the radius step. If the question had been find the radius of convergence in the last example, you would have only needed to do the work that we had on the first page, on page 118. You would have not needed to do everything we did on page 119. Okay? Okay, for the examples on this page, again, I ask that you allow me to explain the example, and then you will be able to write it down. Listen and watch. So let's look at this example here. What do you notice that we have? We have a geometric series, and this is going to converge if the ratio, absolute value of x over 3 is less than 1. Well, we know that that is less than 1 when x over 3 is greater than -1 and less than 1. So when x is between -3 and 3. So we are centered at 0 because there is no x minus c. The radius of convergence is 3. The interval of convergence in this problem, because we're centered at 0, is -3 to 3. Our ratio test is inconclusive. If I were to do the ratio test, I would get that absolute value when I do the limit is 1. So we never check endpoints on a geometric series. Now, for those of you that want to know why, let's just look at it. If I checked endpoints, if I let x equal 3 in my series, I get 1 to the n. The n goes from 0 to infinity. 1 to the n would be 1 plus 1 plus 1 plus 1 plus 1. That's going to diverge. What about if x is -3? I get -1 to the n. Again, that is going to diverge. So if you recognize that you have a geometric series, never check the endpoints. They will never converge at the endpoints of the interval. Take a moment and write down this example. Example 2. What do I see here? What do you think, which test would be the best to use? Well, obviously, the ratio test. So we are going to substitute n plus 1 everywhere you have an n. Show that substitution first, because look what's going to happen. So when I distribute this 2, I get 2n plus 2 plus 1, so x to the 2n plus 3, which means this is 2n plus 3 factorial, and dividing by this is times the reciprocal. And I need to think about, how do I simplify 2n plus 3 factorial? Because I'd like for it to cancel with 2n plus 1 factorial. Well, I'm going to take 2n plus 3 and subtract 1 and subtract 1 again, and there is my 2n plus 1 factorial. Okay, and let us recall x to the 2n plus 3 means x to the 2n times x to the 3. So x to the 2n plus 1 means x to the 2n times x. So that's going to be the simplification I need to make for this factor, and this is going to be the simplification I need to make for this factor. So there's a lot going on here. So I can see that when I simplify this factor down here. The 2n plus 1s will cancel, leaving these two factors. When I simplify these factors, the x to the 2n will cancel, leaving x cubed over x, which is x squared. Now, there is a lot going on there. Now, let us remember, with the ratio test, I need the limit as n goes to infinity of this expression to be less than 1. This is affecting n only. So I can bring the x squared out, and notice I do not need bars around x squared because x squared will be positive. Now, I need this entire expression to be less than 1. Well, what do I know about this as n goes to infinity? That is 0. And we know that x squared times 0 is 0, and 0 is less than 1. It doesn't matter what the x value is. This series always converges. Now, why does it converge? Because I get that the limit using the ratio test is 0. It's not dependent on any value for x. That is less than 1. It is always less than 1. So my radius of convergence is infinity. Why? It converges for all x. Okay, pause the video. Take a moment to write this down. Okay, example number 4. All right, we're going to again employ the ratio test. So here is a sub n plus 1 over a sub n. We can see that this is going to leave a factor of x minus 3 in the numerator and a factor of n plus 1 in the numerator. Again, I can bring that x minus 3 in front since it will not be affected by n going to infinity. What do I know is happening here? As n goes to infinity, that is infinite. So what I get is the absolute value of x minus 3 times my limit here will always be greater than 1, except for one case. Only at 3 will this converge. And why will this converge only at x equals 3? Because when I go into my series and I substitute 3 up there, look what I get. And I have, as n goes from 0 to infinity, of n factorial times 0. That is going to be 0 plus 0 plus 0 plus, and so forth, which is 0. Remember that when you get 0, it converges only at the center of the series. Okay, take a moment and write down this example. Okay, now where we get to something extremely useful with power series. Properties of a function defined by power series. If a function given by the series as n goes from 0 to infinity of an times x minus c to the n is a0 plus a1 x minus c plus a2 x minus c squared plus a3 x minus c cubed plus dot dot dot. If a function given by this has a radius of convergence that is positive, then the interval c minus r and c plus r, in other words, centered at c, subtract the radius, add the radius, then the interval, then on the interval, c minus r to c plus r, f is continuous, differentiable, and integrable. So the derivative and the antiderivative are, okay, if I take the derivative of this, that is a constant, off it goes. The derivative of this term, this is raised to the first power, it's a1 times the derivative of x minus c, which is just going to be a1. What about this one? It is a2, that is a coefficient, times 2, and the derivative of x minus c to the 1 now, excuse me. So let's take the derivative of every term here. The derivative of the constant is 0, so that's gone. The derivative of a1 times x minus c is a1. Remember, this is just a coefficient, times 1, x minus c to the 0, so it just leaves a1, plus a2 times x minus c squared gives me 2a2 times x minus c to the first times derivative of x minus c, which is 1, plus this is going to give me 3a sub 3 x minus c squared plus dot dot dot. So in other words, this series can be written like this for its derivative. So now we are going to anti-differentiate this function. So as we've done, you know, when we have a general antiderivative, there's always a plus c at the end. Let's just slide that on down to the front. So here, anti-differentiating this term gives us a sub 0 times x minus c. Anti-differentiating this term gives me a1 times x minus c squared over 2. This one gives me a2 times x minus c to the third over 3, and so forth. So we can see that anti-differentiating this series is going to be our constant plus, see that can come out in front, n goes from 0 to infinity of my a sub n times x minus c to the n plus 1 divided by n plus 1. The radius of convergence for the series obtained by differentiating or integrating a power series is the same as for the original power series. However, the interval of convergence may differ as a result of the behavior at the endpoints. Also, let us recall when we are anti-differentiating, we are doing that with respect to x, so n is a constant. Of the three series, f, f prime, and the antiderivative of f, the one for f prime is least likely to converge at the endpoints. If the series for f prime of x does converge at the endpoints, then the series for f of x also converges there. Okay, let's look at an example. Again, let me explain the whole thing. I do run out of room on this page and carry it over to the back of the previous page. So again, let me explain the whole thing, and then you'll have an opportunity to write down the example. Here we have, find the interval of convergence for f, find the power series for f prime and its interval of convergence, find the power series for the antiderivative of f of x and its interval of convergence. So again, we are going to take the limit as n goes to infinity of the n plus 1th term over the nth term. Okay, the n plus 1th term, everywhere you have an n, you're going to substitute n plus 1. So n plus 1 gives me n plus 2, x minus 5 to the n plus 1 over n plus 1 times 5 to the n plus 1. Dividing by this means multiplying by the reciprocal, and you have done so many of these, you should be able to get to the simplification easily. Now we can see that I can take the 1/5 out and the absolute value of x minus 5 and just look at this part for my evaluating of the limit, and I know that the limit as n goes to infinity of this factor is 1. So I have that this gives me this. So we are centered at 5. Let's see if we can find a radius of convergence. We know how to do that. So it looks like our radius is 5. So our possible interval of convergence is from 0 to 10. Now we're going to check our endpoints. Okay. When x equals 0, substituting into the original series, I get -1 over n, which diverges. When x is 10, substituting into the original series, I get the alternating harmonic series, which we know converges. So that means that my interval of convergence is x greater than 0 and less than or equal to 10. Now let's find the power series for f prime. The power series for f prime is going to be taking the derivative. So when I take the derivative of this, the n's going to come down and cancel with this n, and that's going to leave n minus 1. Okay, only taking derivative terms that have x in it. And so I get for my interval of convergence, x greater than 0, less than 10. We diverge by oscillation with the nth term test. You can check that for when x is 0. Okay. And now we're going to do the antiderivative. So the antiderivative of that series is -1 to the n plus 1, x minus 5 to the n plus 1, divided by n times n plus 1 times 5 to the n. Remember, x minus 5 to the n plus 1 divided by n plus 1. The n and 5 to the n were already there. Plus that constant c. So we'll check at 0. So our interval of convergence is, we need to check 0 and 10. So when we check at x equals 0 in this series right here, we get -1 to the 2n plus 2, so that will always be positive. 5 to the n times 5 over n squared plus n times 5 to the n. So what we have here, bringing the 5 out, gives us this series, and we know by the direct comparison test that this series converges. The direct comparison test with 1 over n squared. So let's now check when x is 10. And this is the rest of checking when x is 0. Now let's look when x is 10. Again, substituting 10 in gives us this. And again, by the direct comparison test, we have an alternating series that is absolutely convergent by the alternating series test, and then by direct comparison of this with 1 over n squared, we have convergence. Okay, take a moment to write down the work from this example. Here's the bottom of that page. Here's the overflow. Your TPs, 1, 7, 13, and 45. See you next time.